Hello all, welcome back to my third lecture of quantum mechanics QM101. Today the topic is a today we'll take a mathematical interlude because in this lecture we will discuss some of the very relevant mathematical topics which are often used in quantum mechanics. Some of them you might have heard of it, even I gave a link to some of these concepts, but I'm now teaching them explicitly in this video because they are important for certain kind of construction which is important in context of quantum mechanics. So let's get started. So the first thing which we will deal with is inner product. I'm pretty sure I gave a link to for the concept of inner product and inner product spaces, which is the basis for how we define a Hilbert space. But now here I'm going to explain what is a inner product because it's really important to understand. Now as you can see, the word product means that there is some sort of multiplication. So inner product is also a multiplication of two vectors. So you take two vectors from a vector space and you map it, you define a map so which take two vectors from the vector space and give you an element of the field F. This kind of map is called inner product if it satisfies three properties. This is the symbol of inner product. Basically, in place of dot you put the vector or the label of the vector. This is the cat, this is the bra. Okay. So now I'll come to the notation later. First we define the properties. So the first property is it's linear in second variable. Some people define linear in first variable as well, but for our purpose it is going to be important that it's linear in the second variable. Linear in the second variable as in, if I take a vector u and plot it with alpha v plus beta w, then it is same as alpha u v plus beta u w. I might, instead of this line, I might sometime draw a comma because that is also a different notation, but I should stick with this line because it's how we write vectors in quantum mechanics. Okay, so here alpha and beta are the element of the field, and in case of quantum mechanics this field is it's only the field of complex number only, unless there is some very special kind of theory. For general quantum theory we use the set of complex number as the field, and u, v, w, they are the elements of the vector space V. Now inner product, okay, I forgot to mention, inner product is also known as the dot product. It's not really the dot product, it's the generalization of dot product. Dot product is the product which you define in a special kind of vector space called Rn. This vector dot product v dot w, where you multiply all the components and sum it over all the dimensions or the degrees of freedom. That is the dot product which you learned in Rn. Okay, this inner product is basically generalization of that concept of dot product. Okay, so it's a generalization. Now the second property is conjugate symmetry. If you take two elements, vector product, inner product of two elements u and v vector in this order, and you take the reverse order, then they are related but they are not exactly equal. They are complex conjugate of each other. Basically, if you flip the order, if you take, instead of cat v you take bra v, and instead of bra u you take cat u, then it becomes a complex conjugate of the previous one. So okay, and third and the most important property is positive definite. This property is important because it allows you to use one of the very famous inequalities in the concept of linear algebra, that is the Cauchy-Schwarz inequality. And what does positive definite say? That the vector the inner product of two vectors, the inner product of the vector with itself, it can either be 0 or greater than 0. It cannot be less than 0. And not just that, and if it is equal to 0, then it means that you have taken the null vector, and the vector is the null vector. Okay, so these are the defining properties of inner product. Now from this we will define the concept of dual. Before defining dual, I can tell you the standard inner product in the case of complex numbers. So because that is what we are going to use. So as I said, this is generalization of dot product, and dot product is a kind of inner product in Rn. So this is what we call the standard inner product of Rn. The standard inner product on Rn. The standard inner product on, and here Vi and Wi, these are the components of the vector. Components. Similarly, if you take the vector space as C to the power n, then you define the inner product Cn or Cn to C. Basically, you take two vectors from this vector space Cn and you map it to the field of complex number. Then what is the standard inner product there? Suppose the V and W belongs to the Cn, and V is basically a set tuple of n complex number V1, V2 up to Vn, and W is W1, W2 up to Wn. Then or you can write it as like this: V is V1, V2, Vn, W is W1, W2, Wn, then W is. Now here the element which is taken first, like if I write W, then the definition goes like this: summation from 1 to n Wi complex conjugate Vi. Similarly, if you write VW, then it is Vi complex conjugate Wi. You can check that these are complex conjugate of each other. Okay. Now, using this concept of inner product, we can define the concept of dual space. So now our next topic is dual space. Now this dual space is also very important in other aspects of physics, even in classical physics. This is exactly what we call a covector. Okay, but we'll come to that later, like in some other series maybe, if I'm having like that. For now, dual space. What's a dual space? And dual vector. Dual space and vector. So a dual vector is a linear map from V to F, from the vector space to the set of field. Now, and it's not any kind of map, it's a linear map. That is, it takes two elements from V and what did I say? I forgot. So it's a set of from V to F, and it does it linearly, as simple as that. Now there are variety of such maps which are possible. So consider a set of all dual map vectors. Dual vectors as in set of all such map from V to F, all the set of all linear map from V to F. And this is what all the linear map from V to F such that phi is linear. Such a set is what we call V star or dual space. And this dual space has a very interesting property that V star is actually isomorphic to V. Isomorphic as in they have the same algebraic structure. Their dimensions are same, their algebraic structure are same. In fact, for every element in V, there exists a corresponding element in V star. Let's call it phi V for the time being. Now you can find this phi V using, say, if there is a one-to-one mapping from V to V star, you can define such a map. And how you define such a map? You can define such a map using the concept of inner product. So what you do is you take a vector V. You first define a inner product from V cross V to F. Now you want to define a map from V to V star. And what is V star? It's a map from which takes element from V to F. Okay, and that too linearly. Now, so how does it define such a map? Let's call it psi. Psi of V is basically this thing. You put for the inner product, you put the element V in the first place, and the second place it's empty, right? Sorry, I should use it. So let's call as phi V. The V corresponds to phi V. So this psi of V is exactly this symbol phi V, this map phi V, which takes some element from V and gives some output, and this is V. Okay, so if I place W here, that means I take W here. If I place U here, I put U here. So if I write it like this, it's basically this quantity where first element is specified but second is not. Okay, so since we have fixed one of the V, this V is fixed but second is not fixed, so it can be any V. So this is exactly a map from V to F, and it's a linear map because the elements are linear because this inner product is linear in the second variable. That's why that first property was important. So this is what we call a dual of the vector V. But instead of writing it like this, we just write it like this. And this is one of the reasons why we write the vector V as ket V. So what is the bra V? How is it related to ket V? It is that bra V is basically dual of this ket V. This is the relation between bras and the kets. So if V is this element, V1, V2, Vn. So now when it is ket, if you take it from this notation, ket comes at the second number, and when you define the inner product in Cn, you see the second number is not complex conjugate, but the first one is. So when you take W, here we have W1, W2, but when you put the W here, it is Wi prime. So the elements of V is Vi prime, sorry V1 prime, V1 bar, V2 bar up to Vn bar. But we can, why do we write it like column vector? Because if we write V cross V, that means there are two column vectors, and there's no way of multiplying two column vectors in the ordinary matrix multiplication. You can define a different one, but like component wise if they are the same size of matrix. But why do that? Why use a different notation when you can just use the matrix, this simple matrix notation? So instead of writing it like a column vector, we just write it like a row vector: v1, v2, vn. So this is a column vector, this is a ket vector, this is ket v, and this is the corresponding bra v. So this is how you define a dual vector. So note that dual vector is defined using the notion of inner product. If you change the definition of inner product, the dual vector will change accordingly. The dual vector corresponding to V won't be the same if you use different inner product. But the sets, they are isomorphic. That is, no matter whatever you inner product you choose, they will be isomorphic to each other if that inner product has these three properties. Now this concept of inner product. Now this concept of inner product is used to define another very important notion called self-adjoint operators. Now this is a very important concept because this is what we often use in quantum mechanics. Okay, now what's a self-adjoint operator? Okay, so suppose you have an operator, say O, or let's call it T. T is very common to represent a transformation. T is a map from V to V. Okay, let's just do one thing. Let's deal with the self-adjoint operator in the different video because this video is already going long enough. Okay, so this is part of the next video. Here you have to just remember this much: how is inner product defined and how you define a dual vector and a dual space using the definition of inner product. Okay, so I hope you like the video. Enjoying, maybe not, I don't know, it depends on you. What do you enjoy and what you not. If you are watching it for exam, definitely not experiment. But if you are genuinely trying to learn something, I hope you learned something new. So just, if you like the video, just subscribe the channel for upcoming videos. And as I know that I have been very unpunctual with this video uploading, but from now onward I will try to upload at least one video every week. Okay, so let's try to achieve that, and till then, bye bye, see ya in the next video.